Hey guys.
Hey, Mike.
So we've got another withdrawal session planned for today, and we're going to try to cover the remainder of what we weren't able to finish last time. So Mark is going to run through a, um, a kind of an overview of the remaining cases and the different system states, and then we'll jump into how to manually run through that with the simulator.
Mike, you're recording right on your end.
Yeah.
All right, good.
Okay, you guys can see the 15 document.
Mark, you're cutting out just a little bit.
Yes, I
Oh,
can.
really?
I can see it, but you're cutting out a little bit audio.
Okay. Let me know if it gets unbearable, and I might just have to lean on Mike to do it on his end.
You're better now, actually.
Okay, that's good. Okay, so yeah, I said that. So in the previous call, we have a look at one specific case of the withdrawal in detail, and I said that the logic tree that handles withdrawals actually has 6 different components. And I thought it was important to take a little bit of time to explore how that logic operates, because it is pretty complicated. But I do want to draw your attention to the bit 15 document, which actually has all of this explained. I hope in good elaboration, enough to get from no understanding at all to something that is serviceable fairly quickly. And the way that I've structured this, it basically deals with each one of these 6 different situations in order. And so what I'm going to do is basically I've gone back over the bit 15 document. I actually noticed that there's a typing error in here, and I'll fix that. I'll fix that today. But what I've done is I've gone through and I've reread everything that I've written. And I've basically taken each one of these examples as they appear in the document, and I have moved them verbatim into an Excel spreadsheet so that we can point to different cells and have a look at what's happening here. But just for your reference, right, if you're watching this video later or something, and you are, maybe you're reading this document at the same time, and you want to see precisely how these calculations are performed, then I think that this call is going to be the right resource for you. So I'm just going to stop sharing that so that I can begin sharing my V3 spreadsheet. I've also added something that I hope is going to be of some utility, which is this, describing how this arbitrage profit valuation thing works, so that we can prevent exploits. So this is the first example in that spreadsheet. So let's just go over again what all of these different groups are, because there's an object obviously for each one of these things in the simulator. And then we're going to look at how changing some of these numbers affects the logic tree and the associated outputs. So let's just quickly go into that now. We've got a system, a state, where the BNT pool has 1,000 BNT in it, the TKN pool has 1,000 TKN in it, and then we've got some off-curve component of TKN. We're just going to let that be 500. We can see in the staking ledger that there are 1,400 TKN staked, and because we have 1,500 TKN in the protocol in total, that means that we're in a state of surplus, which is what this cell up here is telling us. I'm going to go a little bit into what these other cells mean, and sometimes this one isn't very reliable because of a rounding error in Excel, but that's okay. So based on this state, we know that we're in a surplus, which means that there should be very little preventing the withdrawal of the TKN. We always apply a withdrawal fee, which is set by the network. And again, this is not a source of revenue for the protocol. This helps to fund the insurance mechanism when it was operating. So let's go a little bit into detail here. So again, recap on what we did last session, and then I can go into what happens when we start changing these values and end up further down the tree. So what we do here is we say, okay, we're going to apply the withdrawal fee and give back the amount of TKN that the user is expecting. And you can see here on this output, we're giving back 99.75 TKN, and this is S, right, in bit 15. You can see that it's got there's an equation in that document that tells you precisely how to calculate it. But then what are all of these other parts, and why are they there? So if you think about this, when the system went into surplus, it's the same as saying that BNT is in deficit. And so what the system is going to try and do is use a little bit of that excess to try and recover some BNT from the market by opening an arbitrage opportunity with the withdrawal fee, right? So it's a self-healing mechanism that, as I said in the previous call, we never really had the time runway during the bear market to see how this could operate, but this is the design aspect behind it. So what happens is that the 99.75 TKN removed from the vault, that's true. And that is delivered directly to the TKN liquidity provider. But then we also change the off-curve component a little bit. So you can see we've taken all of that 99.75 TKN that the user received, we've taken all of that off-curve so that we can maintain the actual available trading liquidity as per the DAO's wishes. But then we've taken a little bit extra and we've added that to the trading liquidity. So even though there's a withdrawal happening here, the TKN trading liquidity actually went up. And that is, that's this value here. And you can see that this is the output R, right? And I've tried to keep this nomenclature consistent, both in bit 15 and also in that tutorial example that I wrote and included in Discord. Okay, so then what's this parameter here, P? This is the BNT trading liquidity that's actually being burned from the liquidity pool. And this is interesting. So when there's a TKN that's in surplus and someone performs a withdrawal, it actually deflates the BNT supply a little bit. And it calculates this number such that when the pool has these new prices of BNT versus TKN, if we trusted this last price, then we can calculate the arbitrage opportunity that exists here such that the BNT balance and the TKN balance are returned to their initial prices. And we can then calculate what is the arbitrage incentive for doing that. And so the idea here is that as long as the arbitrage value is less than the withdrawal fee, then there doesn't exist a financial exploit, right? So we're not talking about user experience. We're not talking about anything else other than, whether or not the protocol is protected against potential abuse vectors. And so as long as this number is less than 100%, then there is no abuse, okay? Now, I explained all of these, in slightly more detail in the last session, and I'm just going to quickly remind you why some of these things are the way that they are. The first one here is the constant liability. The constant liability just means that whatever the surplus was before the user withdrawal and after this simulated arbitrage should be the same. So let's have a look at how to calculate that. We know that the TKN balance of the protocol before the withdrawal started was 1,500, which is these two numbers. And we know that the staked amount was 1,400. And so if we divide that and maybe turn this into a percentage, you can see that there's about a 7% surplus or 107% surplus, depending on your preferred syntax. And we want to make sure that at the end of this arbitrage, that this number should be exactly the same. And so if we take that into account, the new balance after the simulated arbitrage is complete, the amount of TKN still left off curve, and then divide that by the new staked amount, right? So if you have a look at the stake balances, we always reduce it by the whole X, ignoring the withdrawal fee. So if our calculations are correct, then we should find that at the end of that process, the actual surplus number has not changed, right? That is critical because it means that this user's withdrawal, it doesn't affect the state of the system for the next user who wants to withdraw after that, okay? And the only assumption that we have to make is that arbitrage is relatively efficient, and that is a pretty good assumption. And as I pointed out in the Bit 15 explainer, it doesn't actually matter if this arbitrage is closed immediately or at some point in the future, because what the protocol is really doing is just repricing one asset versus another. So the arbitrage gets a 15%, a 15% bump due to this. But let's have a look at what happens if we change, for example, the amount of TKN in excess. So if I set this number to be 1,000, for example, you can see now that when we run through these same situations, all of a sudden the arbitrage profit is 680% of the withdrawal fee. And this means that if you were a liquidity provider during this part of the process, you might notice this and then perform a withdrawal and atomically arbitrage that position in order to drive value to yourself, right? And this is the type of exploit situation that we're always trying to avoid. It could also mean that under certain situations, you might be encouraged to deposit liquidity only to withdraw it immediately in order to set this up. So these are the kinds of financial exploits that we need to consider and make sure that we're dealing with. So in that case, what we have to do is move to a case where we're no longer performing this type of arbitrage, and that is the second fork of this logic tree. So we've got exactly the same situation as we did up here. We're only observing that the withdrawal amount is higher than H max, which leads to a higher arb profit, which results in an exploit. And so we move into this part instead. And so here, all we do is say, okay, fine. There's plenty of TKN, right? And so we're just going to give the user everything that they want. We're going to take it from the excess and just leave everything else as it is. So in this particular situation, the state of the system will actually change slightly based on the surplus and deficit. So if we take a look at this situation, we can say that before the withdrawal occurred, we had 2,000 TKN in the system per 1,400 staked, right? So we have about a 42% surplus. Whereas after this withdrawal has occurred, we have 1,900 divided by 1,300, which means that the surplus is going to go up just a tiny amount. And so this isn't terrible, right? Because it means that it just means that there's more TKN for the next liquidity provider who withdraws. And if you want to think about it this way, you're kind of giving the system a little bit of runway. It does mean though that the apparent or the implied B&T deficit is not being addressed in this case. But it's a small concession to make rather than having something that's easily exploitable. Okay, so then let's have a look at what happens when we move some of this, right? I want you to realize that in both of these situations, the program is doing everything that it can to try and keep the trading liquidities exactly where they were, right? And that means that if there's off-curve liquidity to use, it will always use that first so that there isn't some sort of sharp change in the available trading liquidity for the TKN that someone is trying to withdraw from. So what we can do is we can change some of these balances around so that we end up with basically the same distribution of tokens. There's slightly more BNT now because there's more TKN trading liquidity, and there's there's a lot less in the excess, but there's still a total of 2,000 TKN, right? We didn't change the number of TKN in the system. And the overall surplus hasn't changed because the staked amount is still the same. But you can see that if we're in this situation, then there actually is insufficient TKN off of curve to support the withdrawal. And so that means we're running into negative numbers here, which is obviously impossible. You can't have negative tokens associated with the balance. And so in this situation, we move into the surplus default exposed pathway. So this is the third leg of the withdrawal mechanism. And so what this one does is it says, fine, we're going to take what we can from the excess, right? So we're going to let this number run down to 0. And then whatever's remaining, we're going to take from the trading liquidity. So you can see that only is the trading liquidity balances actually touched as a last resort, only if the protocol doesn't have anything left in the excess to fund this withdrawal. And again, you can see here what the outputs are changing quite a bit. So in these other examples, right, we had BNT liquidity that's being burned from the pool. We had TKN being added to trading liquidity. We had TKN removed from the vault. In the case where we're covering it exclusively with the excess, then you really just have to remove TKN from the vault. There's not a whole lot more left to do there. But in this case, you've actually got to do quite a lot. And that's because as you're removing TKN trading liquidity, you also need to remove BNT trading liquidity. So we're still burning BNT. The protocol then has to renounce ownership of that BNT. We have to remove TKN from the trading liquidity, and then we need to return all of those TKNs back to the user. So this is the last ditch effort of the protocol to, with regards to surplus logic. But you can see that, at least from a logic coverage perspective, this actually takes care of all possible states of the system with regards to surplus. So that covers half, right? Half of all of the withdrawal logic is dedicated to surplus, and then the other half of the withdrawal logic is dedicated to deficit. And so in this case, again, this is the example straight out of bit 15. We're looking at a situation where the protocol has a mild deficit. So we've got 1,000 BNT, 1,000 TKN in the pool, plus 800 in the excess, so 800 off-curve liquidity. And if you have a look at that number plus that number divided by the total stake, right, you can see that there's about a 10% deficit here. So what does the protocol try to do? Well, in this case, it does the opposite of what we did during surplus. So instead of burning BNT from the pool, which is what we tried to do up here when this was 500, okay, instead of burning 7.35 BNT in the pool, in this case, what it's going to do is it's going to mint 9.826 BNT to the pool. So here, we're going to take a small amount of TKN trading liquidity from the curve and take a small amount from the excess and give that to the user. And then we mint BNT into the pool in order to create this arbitrage opportunity. And again, we perform the same logic as before to try and work out whether the arbitrageur is receiving an unfair advantage during this situation. And as long as whatever the withdrawal fee applied is less than what the arbitrage value is, then this is allowed. And again, remember that as long as the withdrawal amount is less than H max, that's what this parameter is, then this should hold true. And I can prove that to you right now by letting the withdrawal amount be H max. And you'll see that the arbitrage value should hit exactly 100%, right, which is the maximum threshold. So in this case, as long as this is less than H max, then we can allow this process to occur. We mint just slightly less than 10 BNT to the pool. We remove a small amount of TKN from the trading liquidity, and we remove a total of 99.75 from the vault. So that's sent to the user. The arbitrage opportunity is created. The arbitrage opportunity is closed, and that means that when we then take this new number and add it to the excess, so this is now the total TKN in the system, and then divide that by the total staked amount, we see that the overall deficit has not been affected, which is precisely the behavior that we're trying to achieve. Okay, so what happens though if we increase the staked amount a little bit, right? So make the deficit slightly worse. So if we increase this to like 2,200, for example, you can see that that's enough to take the ARB profits to 116%, which means that there is an exploit opportunity here. And you can see H max is automatically updating to to reflect the new maximum withdrawal amount that this logic can support. So now that we're over that amount, we move into this situation, and that is the user is withdrawing a certain amount of TKN that's equal to or less than the off-curve liquidity. So we're going to do the same thing here, but we can't let the deficit get any higher, right? This is when the BNT protection mechanism used to kick in. So I can show you what that looks like right now. If we take this number and add it to this number and divide it by this number, we get the total deficit for this particular situation. And we want to make sure that that number is the same afterwards, right? So that the user performing this withdrawal isn't putting the other users at a disadvantage. Okay, and we can see actually if I increase the decimal resolution here that these numbers are exactly the same. So we can calculate precisely how many TKN they can receive of this 100, such that this remains true, right? Such that the deficit doesn't increase. And when the BNT distribution was switched on, what we would do is then calculate what the difference is between the TKN that we can take out of the system due to this mechanism and the amount that they should have received, and then use the spot price on the pool to calculate how much BNT that they should have. So I can show you that now. If we take this number and we multiply it by 1 minus the swap fee, which should be 0.005. I mean the exit fee, sorry. We see the user should be receiving 99.75, right? They received 81 TKNs in total, and the difference between those two numbers is 18.13. And because BNT and TKN in this particular situation is worth exactly the same amount, then that's the amount of BNT that they should receive, and that means that the total protected valuation of their position is maintained. Obviously, we can change this amount, right? If BNT was 2,000 or something, then you can see that we multiply it by that price in order to calculate that the amount that they should receive in compensation. And so that's what these outputs are. So we haven't seen this output yet, which is output T, and this is the BNT received by the user. Okay, so this can be done if and only if there is enough TKN in the off-curve liquidity to provide the user their full withdrawal balance. So what would happen then if we did the same thing as before? Let's increase the trading liquidity a little bit and move the TKN excess. Okay, so now the user is still trying to withdraw 100, but there's only 50 in the off-curve liquidity. So if we, again, use this logic, then the protocol will try to remove more TKN from the off-curve liquidity than exists, which means we end up with a negative number. And obviously that can't be allowed to happen. So here's that exact same situation now, but using what we call the exposed logic, which means that the protocol will take what it can from the off-curve liquidity, and then take the rest from the trading liquidity. So again, it will only reduce the trading liquidity as a last resort. Everything else that I've said is still true. So the overall deficit isn't allowed to change or isn't allowed to be worsened by this user's action. And you can see that there's a lot going on here. We are burning BNT from the pool because the trading liquidity is being reduced. The protocol then needs to renounce ownership of that BNT, which means essentially burning its own pool tokens. We know that we need to remove TKN from the trading liquidity, from the vault, and we need to mint BNT and send it to the user. So this is this is by far the most complicated example, and kind of ties up all of those different conditions together. So I think what we're going to do now is I'm going to stop presenting my screen, and Mike is going to hard code some of these situations into the simulator. which is going to be helpful if you're learning how to use the simulator commands, and then actually perform some of these withdrawals to show that the simulator is producing exactly the same results that you just saw in the spreadsheet now.
Great. Let me know if everybody can see my screen okay. Anybody?
Not yet. Okay, yeah, I can see it now.
Okay, good.
Yeah, it's good now.
All right, so I'm just going to make this a little bit bigger so we can kind of refer back and forth. What I've done is created a new notebook, which is which does a couple different things, right? So it kind of runs through the normal situations that we've done to get the simulator up and running. But then about towards the bottom of it, I put in a new section which examines the withdrawal algorithm from a couple different perspectives. And one of which is like after we run through, Alice doing some withdrawals, like very similar to what we saw last time. At that point, we can examine the withdrawal algorithm workings in a lower level of detail by kind of manually starting up this withdrawal algorithm class, right? And we can extract the inputs that we need to use this class based on the existing state. So we can say, get the existing trading liquidity for BNT TKN, get the TKN excess, stake balance, so on and so forth. And from that point, we can initialize this class, and we're just going to call it solver, right? Because it's basically going to perform the calculations of the algorithm based on the state of the system. And then we can just once we've loaded up those existing values, we can just call this method process withdrawal, and have a look at what those outputs are. Now that's good for anybody who wants to basically run through the higher level API or interface, so to speak, with the simulator, doing different scenarios, and then get a lower level look at what's happening behind the scenes. But for the purposes of following along with the BIP15 document, it's going to be more helpful to just manually override these values, right? So instead of using the actual state of any pre-derived system with users and so forth, we can just say that the BNT trading liquidity is whatever, and the vault balance is such and such. And this we can follow along with the BIP15 document quite a bit easier by doing it this way, right? And I'm just going to try to look for one of these scenarios here. So putting those values in here, like for instance, we can define what our withdrawal fee is, our BNT trading liquidity of, for instance, 1,000, and TKN trading liquidity of 1,000, along with a stake balance of 2,000, right? So stake balance is 2,000, BNT and TKN trading liquidity is 1,000 each. Our vault balance is 1,800. And so we can put our vault balance here is 1,800. This vault balance is not used directly within the withdrawal algorithm class, but we can derive the TKN excess value that is used directly as long as we have it. And then we can basically run through these scenarios by just and by the way, I'm using like a slightly different so I'm not using Jupyter directly this time, if anybody who's been following along notices, but this is actually PyCharm. It's an IDE, so don't let it confuse you. But it's running the same Jupyter notebook, just in a little bit more convenient user interface for me to work with. so we can look here and see what the resulting output is for these different states. Now I've so TCAN sent to user 89, 7750 and 9750, right? And we come out with 99.75 for the total sent to the user. So TCAN sent to user 99.75. Now, one thing that's a little bit different here when you're going back and forth is, these staking ledger balances and vault balances and so forth are updating, right? So if we were to process this withdrawal, at like the Bancor DApp class level, within the simulator context, we would end up with these, exact resulting balances. Now, in order for you to, to derive those, again, basically you would need to add these outputs that you're seeing here to the existing system state to kind of like marry the two values, so to speak. And for the purposes of today, we're not going to have time to or necessarily even want to get to like that level of, it's just a bit confusing to follow. You need to spend a little bit of time going through, the having users perform these functions and then kind of breaking it out like this. But it's totally possible for that to be done. What I've done here is created like a couple of these manual situations which coincide with what's happening in the BIP15 document. And you can see like we end up with TK sent to user of this 8161 here, and we've got the same balances shown in the output of the BIP15 document. You can, of course, like do these tests for, is X less than H lim, is X less than H max, and basically arrive at these same conclusions. And then, of course, the caveat is that like there are a couple small deviations which I think you'll potentially pick up on if you go through it in extreme detail, but for the most part the results are going to agree. And you can rest assured that like with the simulator output values that we have done some pretty extensive testing at this point to in fact, every time there's code checked into the repo, it runs a series of tests against actual contracts, logic, so that we can validate the results of the output here. So in the event where you do see some disagreement at this point, I would say you should assume that in the event of disagreement, the simulator is actually giving you the values that the contract will give you, and there may be a couple of minor typos in the BIP15 document. But yeah, I think with that we've got we're about 5 minutes over. I'm going to push this again. So this is going to be called User Action State Transition Functions Part 5 of N. I guess I'm going to put Part 5 of 5 because today we're essentially finishing covering the user action section. And I just want to, before we call it here, refer to where the I'm going to pull up the project structure, and if we look in the spec directory of the simulator, and we look in actions.py, that's where we're going to find this withdrawal algorithm. You can now also look at the different methods which are associated with, I think the BIP15 document, first of all, let me call attention to one thing I've noticed, that we have like HMAX surplus and HMAX deficit, which were kind of like the original the original behavior of the system as it's outlined, I believe, still in the BIP15 documentation. However, you'll notice here, like retroactively due to changing contracts, this HMAX deficit is basically returned as zero, and we're really just relying on this one to go forward with the logic. But it's these are just changes that kind of happened after the fact. They're then run through all 6 of the different combinations of situations, between like which state of the system you're in, whether you're in a withdrawal or a surplus, and the corresponding protocol logic that should be taken given the existing situation. And so we call these different things like arbitrage withdrawal surplus state or condition, default withdrawal surplus covered, and default withdrawal surplus exposed. So Mark mentioned, when he was talking, these same terms, and you should find a lot of agreement between the Excel spreadsheet that Mark was just referring to, and the specific names of these conditions that he was using are going to, basically align with what you see in the simulator. Now, and then you can follow from this point and see exactly where this standalone class, which you'll notice is like independent of the existing state, right? So like we don't see in here, we're not passing in the state as an input, and we're basically just using these derived values. So now, if we do use this withdrawal algorithm within the context of, a withdrawal, and we go to process this withdrawal, then you can follow like where exactly is this being used, and you see like, okay, well, yeah, if the token that we're trying to withdraw is not BNT, in other words, if it's ETH or any other TKN value, right? Then as long as the cooldown period is complete and the price is stable per the EMA, which Mark also referred to, then we can basically update the state to say that we're now going to complete this withdrawal, and from there get the input values that we need to perform the withdrawal algorithm. We're going to initiate the class, and we're going to process this, right? And so and one more thing, so if we go to this process withdrawal, it's like the very last method in the withdrawal algorithm. We can basically run through these different conditions, which Mark referred to, some, or I guess all of them at this point as well. So when these conditions are met, then these particular methods are going to be the logic that's used to complete the withdrawal, right? So this is like the main conditional logic of the class is this process withdrawal within the withdrawal algorithm, and that is going to run through which of these 6 conditions is the current state based on the values that are passed in, and then it's going to hand this off to the respective method to complete the calculations, and then return back these values, which will then be used to update the state, right? So that's in potentially a fire hose full of information there to run through pretty quick, but I just want to draw your attention again to checking out the actions.py file within the repo, and relating this to the user actions accordingly, right? And that's how you'd go about doing that. So with that, I'm going to call it here, and unless Mark or anybody has anything else, we will pick up again next time. And continue on.
What have we got on the next one?
Yeah, that's a great question. I was